Find out. I did. I pushed the record button. I pushed the record button. So there we go.
Starting tomorrow, or Friday, whoever reminded gets $5 more.
Right, Okay, we're going to the document camera. Yes, sir.
I had a question on the homeworks. Are we getting the 10% if we get it done 48%?
You
or
should
48
be.
hours in
You
advance?
should be, but I don't know if it's exactly set up that way.
Well, 'cause I don't think I've been getting it for the pre-work.
Well, one pre-work was due Friday.
They're both due Friday.
Okay.
And I had most of it done before.
Okay, I'll look at it. Just send me an email to remind me, because that 10% bonus is still out there.
I get it, I'm good.
Yeah.
So once you
Well, and I think that was a WebAssign problem.
There should be a
Yeah.
extra.
And it may also be a Flash problem. Yeah, I'm not, but I don't think Flash is a, all right, why is this one, now if I come back, I had to play with it.
So you can see 0.5 out of 0.45.
Okay,
This is the
and
question.
turn it off and turn it back on.
Right, no one got you.
Like that'll
It
show you
just
how
didn't
much
look like I was
everything's
getting
worth.
it. Yeah. 'Cause it was-
We're having trouble getting the document camera to come up on the screen over here.
Sometimes I think you have to disconnect.
Well,
and re-
I made it work on Monday.
I don't mind how they do it 12:30.
That might help. Let's try that.
I barely missed it.
Woohoo, there it's on there. They can see it over there.
I haven't started the homework yet.
The document camera's there. Got that?
Oh,
Okay, now we come back. Oh, technology's fun when it works. It's crummy when it doesn't. Oh, oh. Yay, woohoo!
What happens when solar flare wipes it all out?
Well, then we all just go back to sending smoke signals. Okay.
I have a question on
Uh-huh.
the books. Like, you said for computer concepts, we're supposed to have like a book online, right?
I don't know if it's online or not.
Oh, you don't?
Not for computer concepts. I have no idea. All I know is that they were getting things through Cengage.
I
Well,
think,
because I opted out of it.
Yeah?
but then,
yeah, we get it.
I mean, I didn't know where it was supposed to show up at.
But you can
But then
actually
I have
add.
physical books.
Yeah, but you can actually, any Cengage book, you can go in, even if you're not with a class, you can add that book from their library.
Oh, okay,
So you can actually go in and take the title of the book and search for it and add to it.
okay.
So any Cengage book, you can add to your library.
I'll have to look.
Yeah, that's another way to do it.
Because I just didn't know if like, because I know the physical book was included.
Right.
But then I didn't know.
And you're in Ms. Harmon's class?
Yeah,
You may need to go talk to her specifically. All
okay.
right, you guys got questions over there? Because we're about to start. We're going to rock and roll now. And I will be over there in a lovely class with those two guys on Friday. And we're doing lab after class on Friday. Okay? Now they get me to write the lab reports for them. Because I'm their lab instructor. All right, you had another question?
You know, question one on the homework, that's what to do with derivatives.
It's okay. It's all right.
Okay,
It may resolve itself after today's lecture.
okay.
It may resolve itself after, and if it doesn't, come see me tomorrow afternoon and I'll help you guys with it. Okay. Alrighty, so we're starting. So we started playing with good old Hooke's Law. And I'm going to draw my lovely spring here. And we're going to attach our mass. And we're going to do the horizontal thing. So if I call this the equilibrium point for my spring, and I get this is the one where I have the equilibrium point. And then this is when the spring is nicely compressed. this goes from minus x to x, and this is my 0. Right? We know springs work that way. And so if I'm looking at this when it's in motion, initially it's going to go up that way, and it's going to come back this way, and ultimately we're oscillating back and forth like that, right? We've played with it. We know springs bounce up and down. We know that that's how that works. Things that we remember, right? We remember that Hooke's law. F is equal to minus kx, where this negative comes back from the fact that that's a restoring force. That's where that negative comes from. We can calculate spring constants if we know information about the force. We can do that. But if I've got this bouncing back and forth, we can call this distance the amplitude. Now the amplitude is going to be going from here to there, from that portion right there. That's going to be going from there to there. That's my amplitude. It's not the entire thing from minus x to x. The amplitude is just that spot. And we know that if I were to put a marker on there, that if I were to draw it, and I'm going to start at 0, and I'm going to go back and forth like this, that if that marker were drawing, I'd get something that would look like that, right? I get something that would look like that. I'm going to stand out. This is going to drive me crazy. So I get that nice function. And we've all seen that function, right? We know that function. What is that function? It's going to be sine or cosine. Okay? It's going to both give me that function. So now let's look at something a little different. So we've got our spring. If I have my pendulum will go up and back all the way, right? And we know a period is a complete cycle. It's one up and one back. That's the time for a complete cycle. We're going to use t. That's going to be period. And that's the time for one complete cycle. And we've seen that before. And we know that period is related to frequency by 1 over the frequency. And if period is in seconds, frequency is in 1 over seconds, which are hertz. And we've seen that before. And now, if I look at I got my circle. And if I have my object, and we're going to have that object moving around on a circle with a fixed radius, so the radius is fixed, we know that if I'm looking on the x-axis or the y-axis, that we can deal with this right here. There's my angle, right? And this projection there is going to be cosine of my angle, or x cosine of my angle, or r. And we know that the projection over here is going to look like my r sine of my angle. And if I follow the motion of this bead or the motion of this projection, we know it's going to go back and forth along the x-axis, and we know it's going to go back and forth along the y-axis. And that looks an awful lot like circular motion. And just to remind everybody, my circular motion is going to be 2 pi times my frequency, or that's 2 pi divided by the period. So whether I'm going around in a circle, as long as I'm not changing radius, or I'm swinging back and forth on a pendulum, or I'm bouncing up and down on a spring, it's all going to have a motion that I can describe with that kind of a function. Okay? It's all going to have that same kind of function in motion. Now, depending on which book you pick up, ours happens to use cosine. The lab that you guys are going to do today happens to use sine. It's still going to have that kind of behavior. All right? So let's play with a couple of things. First thing that we know that if I'm doing this, I'm going back and forth here, or I'm going back and forth there, the height of that particular function is going to look like a cosine of the angle or a sine of my angle, where that a is the amplitude. Right? And the reason we can do that is because if I look at cosine or sine, cosine is going to go from -1 to 1. Sine is going to go from -1 to 1. That range in my equation there looks like my function. The maximum cosine can never be as 1. The maximum sine can never be as 1. And we know if we do this, so I'm going to draw this. And if I'm doing just the cosine, that's my cosine function, right? Because cosine of 0 is 1. That's one complete cycle. I go from peak to peak, trough to trough. It's one complete cycle. Now if I put my sine function on there, that's my sine function. Because the sine of 0 is the sine of 0 is 0. The sine of pi over 2 is 1. Now, let's remind ourselves of a few things. Okay? We're going to play the mathematics instructor right now. We're going to remind ourselves of a few things. That the sine of the negative angle is going to equal the negative sine. That the cosine of the negative angle is equal to the cosine. This is all in the appendix of your book, to just kind of remind you. And because that's that, then it's easy to know that the tangent of the negative angle is going to be minus the tangent. So it's trig identity, just a basic trig identity. Several of the other basic trig identities are as follows. That the sine of 90 degrees minus the angle is equal to the sine of pi over 2 minus the angle, which is equal to the cosine. Basic trig identity, they're 90 degrees out of phase with each other. And I can do the cosine of 90 degrees minus the angle, which is going to equal the cosine of pi over 2 minus the angle, which is going to equal the sine of the angle. They're 90 degrees out of kilter with each other. I can also write it like this. I can do cosine of the angle is also equal to sine of the angle plus 90 degrees. There's no difference in that. That's one of the things that I have. And I'm going to go ahead and give it to you because we're going to use it later. Sine of any angle plus or minus another angle is going to equal sine alpha cosine beta plus minus cosine alpha sine beta. So the plus gives you the plus, the minus gives you the minus. Because then if I do cosine of the same thing, plus or minus beta, this is going to be cosine alpha cosine beta minus plus sine alpha sine beta. And we'll ultimately use this later on. But since I'm going over trig identities, I'm going to throw it out there for you. Okay? And since we're reviewing math, I'm going to review a couple of special derivatives. If I have the derivative with respect to x of the natural log of x, that's going to be 1 over x. If I have the derivative with respect to x of sine x, that's going to give me cosine x. If I have the derivative of cosine x, that's going to be negative sine x. And then using the train rule, if I do the derivative of e to the u dx, I get e to the u du dx. This one right here is the important one we're about to use. Okay? That one right there is the important one we're about to use. So again, it doesn't matter which one I use, whether I use the sine or the cosine. It's all about where I start, and that phase angle is going to tell me where I start. Yeah.
What is that,
It's the derivative of e to the u is e to the u with the derivative of u to the x. Okay? All right, so if we go back to our spring system, okay, my handy dandy spring system. There's my handy dandy spring system. And this is now in motion. I can write, and we're going to use the convention where I'm dealing with the cosine. I can write a function of x with respect to time as equal to the amplitude, how much of the stretch in the spring that I gave you, cosine the angular frequency times time plus a phase angle. And essentially all I did was just go in and I picked a mathematical function that fit the curve that I got. So when you guys are doing your lab today, you're going to go into, and you guys on Friday, you're going to go into the Logger Pro and you're going to get that. You'll see this on the position versus time graph. Spring will have been bouncing up and down. You'll get a position versus time graph and you'll go in and you'll select, and I want to look at the best curve fit that matches this function. Now the really cool thing is, it's already told me something. Once I get this, I can read the amplitude directly. How big is the stretch? I can just read it right off of the function. I don't have to measure it, I just read it right off the function. I now know the angular frequency because I'm reading it right off the function. Well, if that becomes 3 times t, because that's what my curve fit said, well, now I know that omega is equal to 2 pi times the frequency, and if that's 3, that's equal to 2 pi times the frequency. 3 divided by 2 pi is going to equal the frequency of the oscillation. I can read it directly right out of the mathematical equation. The mathematical function that I fit, I can just lift it right out. Conversely, by fitting it, I can go in and I can say, okay, what's the time that it takes to go from here to here? That gives me the period. I know the period is 1 over the frequency, so I can figure out the frequency is 1 over the period. And then I know the height because I can actually measure this. I can write my mathematical function. So what's going to happen to you as a couple of your homework problems is literally, I give you a function, and let's do one. I give you a function. Okay, we're going to give you a function here. Okay, I give you a function that looks like this. The position of, and this is a piston, so here's the actual problem. I've got a piston in a cylinder. It's described by this equation that 6 centimeters cosine 3 times time plus pi over 7. It describes the motion of this piston. Okay, describes the motion of this piston. So I can figure out where that piston is at any point in time by looking at this. So if you ask me, well, what's that time? What's the position when time is equal to 3 seconds? All I got to do is plug in 6 cosine 3 times 3 plus pi over 7. Plug that into the calculator, and I think that works out to be minus 6 centimeters. So it's going to be at the bottom of its stroke at time is equal to 3 seconds. Now, if for some reason I wanted to know what that stroke was, and I'm looking at that stroke from the center point as 0, so it's going to go as high as 6 centimeters, it's going to go as low as minus 6 centimeters. That right there is the amplitude. I just read it right off of the equation. Now, if I want to know the frequency of that piston, well, guess what? This one does happen to be my angular frequency is equal to 3. That's equal to 2 pi times the frequency. Frequency is going to equal to 3 divided by 2 pi. And when I do that, I just left it that way. And if I want to know the period is 2 pi over 3. I can read it right out of the equation. I don't have to do anything fancy or special. Okay. So let's go back and let's look at this. Couple of things we know. Right? Couple of things we know. One of the things I'm always going to want to know is the velocity at which things are bouncing up and down. We've got position now, right? There's my position. But let's look at it before we actually figure out what the velocity is going to be. Now, if I'm up here at the top, what's my velocity? 0. Because it's going at the very top of its swing, it's changing direction at 0. Where's my maximum velocity? Right there through the middle. And that one's going to be 0 as well. Okay? So guess what we do? So we know that velocity with respect to time is going to equal my change in position with respect to time, which we also know that becomes the derivative with respect to time. So if I'm going to take the derivative with respect to time of A cosine omega t plus my phase angle. Okay? And if I do that, my velocity with respect to time becomes minus A omega sine omega t plus my phase angle. That's my first derivative. Because I got to use the chain rule. I can't just use the t. That's constant, which is why the derivative goes away. And I got to put my omega in front. And we know that acceleration due to time is going to be my change in velocity with respect to time, which is going to be my second, it's going to be that derivative of velocity with respect to time, which is going to be equal to my second derivative of x with respect to time. And if I do that, I get my acceleration with respect to time is equal to minus a omega squared cosine omega t. And my guess is that now clarifies that first two problems that you guys were worried about on the derivatives.
Once I have time to like look at it.
All right, so we can go back to this lovely. That's d to the second, it's the second derivative. That's how you write a second derivative. All right, so we're going to go back to this problem right there. And if I want to know the velocity of my piston at any given time, guess what? My velocity of my piston at any given time is going to be 6 times 3, because that 3 is coming from right there. It's going to be negative because the derivative of cosine is a minus sine. Minus sine omega, or 3 times time plus pi over 7. And if I want to find that velocity at time is equal to, what one I did it at? I did time was equal to 5 seconds on this one. So I'm going to get my minus 18 sine of 3 times 5 plus pi over 7. Plug that into the calculator and I end up with a negative 4.6 centimeters per second. If I want to find the acceleration is going to be minus a omega squared cosine omega squared plus the phase angle. That means if my amplitude was was 6, there's my 6. My omega was 3, so that's got to be squared. My cosine is 3. There's my time plus my phase angle, which is pi over 7. And if I'm doing that for time is equal to 2 seconds, that number works out to be a minus 53.3 centimeters per second squared. And if I remember correctly, one of your problems is the piston problem. Or it sure looks a heck of a lot like it. Can't remember if the piston problem is a general physics or an engineering physics problem. But you've got something really similar. Okay, let's take this another step and let's look at it from a physical system point of view. I've got the Earth out here, and we got a satellite traveling around the Earth. Okay, we got the Earth, we got a satellite. The satellite has a period of 90 minutes as it goes around the Earth. We're actually going to look for the radius. That's what we're actually looking for, is the radius. And I've now given you enough information to find the radius. I'm being cruel with you. Because somewhere along the way you're going to go, okay, all right, so I've got the period, and I gotta find the radius, and I'm going, all right, what on earth am I gonna do? Well, I can do a couple of things. One, you might be asked, what's the angular frequency? Well, that's easy enough, because that's gonna be 2 pi times the frequency, which is 2 pi divided by the period. All I gotta do is convert my 90 minutes to seconds, which makes that 5,400 seconds. And I can actually calculate the angular frequency now, and that becomes 0.00116 hertz. And I haven't done anything terribly fancy. But if I want to find this radius, I might have to do something a little fancy. Good old Kepler's law. That said that the period, there was a constant times the radius cubed. And that constant for things that rotate around is like 4 pi squared big G mass of the Earth. So now all I got to do is rearrange it and solve for R. So if I solve for R, that's going to give me big G, mass of the Earth, divided by 4 pi squared, period squared, cube root of that. You don't happen to remember G. G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Mass of the Earth is 5.98 times 10 to the 24th kilograms. Plug all that back into there, and I end up with the radius is 6.65 times 10 to the 6th meters. Ten 24th. Okay, now we get to do some fun fancy schmancy stuff. Now we talked about the fact that my spring, depending on how it is, that K is related to the spring. It's kind of a material property of the spring. And we know that force is equal to mass times acceleration. And then Hooke's law is minus kx. So I can rearrange this to come up with a function for acceleration. And now we can start playing with the math. Okay? So I'm going to play with the math because we have a function for x. And that's my amplitude cosine omega t plus my phase angle. And we have another expression for A. Okay, everybody with me? All I did was just substitute a couple things in. So now comes the fun part. I can get rid of this because both sides have a negative. I can get rid of the amplitude because both sides have the amplitude. I can get rid of cosine omega t because both of them has cosine omega t plus the phase angle. And I'm left with omega squared is equal to k over m. And if I want to go ahead and take it one more step, I get that it's k over m. So if I have a simple spring system, I can predict what the angular frequency is going to be by using the properties of the spring. This comes in very handy in the real world. We can play with this a little bit, and we can actually show that my acceleration is going to equal minus omega squared x, and this is called an oscillation equation. And it's coming from the exact same form right here. All I did is instead of, I'm just plugging this in for that right there. That's all I did. This oscillation equation you see over and over and over again. It's called the simple harmonic motion equation. We see it a lot, and we run into it in lots of different places. You're going to run into it over and over again. Okay. All right, I want to do one more thing so that you guys get prepared for the homework there. And that's probably all we're going to get to have time for today. There we go. So here's my system, right? If we remember that I have conservation of energy, the total energy here is going to equal the total energy here, which is going to equal the total energy there. Remember that the potential energy associated with the spring is 1/2 kx squared. So if I do the total energy at this point, the total energy at this point is going to equal 1/2 Ka squared, right? Because I'm at the maximum amplitude, that's my maximum x. Here I don't have any kinetic energy because the velocity is 0. So at this point in my system, the total energy is going to equal 1/2 Ka squared. Now, at any other point in the system, it's going to look a little different. So let's look at the total energy of the system. It's always going to be the sum of the potential energy of the spring plus the kinetic energy of the system. Because I'm using conservation of energy. And if I can figure out what the total energy of the system is, which we already did, it's going to be 1/2 Ka squared. I can now put into the system the potential energy, which is going to be 1/2 Kx squared. And I can add in the kinetic energy of the system, which is 1/2 mv squared. That's the energy of the system at any given point in time. Now,
Is that a symbol after the first 1/2?
that's K. These are K's. That's my spring constant. So one of the first things I can do is clean this thing up. I can get rid of the halves, right? So now I've got Ka squared is equal to Kx squared plus mv squared. And depending on what I want, I can write for the velocity at any given time. And so this is the velocity at any position. So I'm going to solve for v. So I get mv squared is equal to Ka squared minus Kx squared. I get v squared is equal to Ka squared minus x squared divided by m. And then I can do v is equal to the square root of k over m a squared minus x squared. And that gives me my velocity at any position.
Is that just minus x?
Yeah, it's minus x squared. When I went to write the x, it was ookie. Okay, in the interest of time, I'm going to cut out some gory steps because we've done it before. So I have a pendulum, right? And we have a pendulum and it goes in this way. A couple of things is, one of the things when we dealt with the pendulum, we talked about that angle. And for my pendulum to really, really work and work properly, sine of the angle had to be small, approximating equal the angle. And if we did that, we could use the force related to my tangential acceleration, mass times my tangential acceleration, and we could get the minus mg sine of my angle, which is going to equal m times my acceleration. M's go away, and we get that g sine g theta. We ultimately could get this expression, that the period of a simple pendulum was equal to 2 pi, the square root of the length of my pendulum divided by gravity. We do this one often enough that if you feel like you need to go back and see it, it is in your text. It's in your text a couple of different places. But we ultimately get, for a simple pendulum, where I have no mass really related to, or the mass of the bob at the bottom is significantly higher than the mass of my string, that I can get my period of my pendulum just with that expression. And this is a simple pendulum. Well, towards the end of Physics 1, we don't live in a simple world anymore. We live in a real world. And in a real world, the simple pendulum doesn't quite always work. And so we're going to get something for a physical pendulum. Okay? And so a physical pendulum might look something like this. I've got a little bit of a string and I have a cylinder or a mass of length L that's swinging back and forth. And if I do that, we know that it's going to act through its center of mass. And it's not going to behave quite like we expect. Okay, it's just not going to behave quite like we expect. Now, the analysis that gives us a simple pendulum using force times mass times acceleration, we can do the exact same analysis using our rotational motion equations. Torque is equal to my moment of inertia times my angular acceleration. Do the exact type of analysis, and it is outlined in your book. It's in chapter 16. It is outlined in your book, but I've got 3 minutes before they cut us off over there. You can actually get to my period, and I'm actually going to do it as omega. So this was this, and if I do this, I get omega works out to be, the angular frequency works out to be gravity divided by the length. Okay? If I go through this analysis, my angular frequency for a physical pendulum is going to equal the square root of the mass times gravity, the distance to the center of mass, divided by the moment of inertia. And when we come back on Friday, we'll do a couple of those real physical pendulum problems, plus another inclined plane motion problem. Cool stuff. I love the bar monitors. Awesome. I gotta catch you. Huh?
You're gonna give a talk.
Alrighty, guys. I'll see you guys on Friday, and then we'll do the lab right afterwards.
All right.